Nuclear Quest and Old Gold, we're going to talk about nuclear reactions. We should be able to do all these objectives. The key things are, in chemical reactions like we talked about, they occur in the electron cloud. The atoms itself remain intact. You have the same atoms that you started off with that you end up with. Meaning the nuclei of all the atoms are the same. Elements present at the start are always present in the end. And mass is conserved. In a nuclear reactions occur in the nucleus. That's why they're called nuclear. The atoms themselves are changed. The nuclei are changed, and we have new elements that are produced. And mass can be gained or lost. So if you think about this in terms of Legos, a nuclear reaction would be like breaking a Lego apart, like one single Lego and making a new Lego into that. Whereas chemical reactions are just putting Legos together and taking them apart. So here's an example of a chemical reaction. Yes, but wait. Here's an example of a nuclear reaction. Notice in a chemical reaction, we start with, in this chemical reaction, we start with one magnesium atom, two hydrogen atoms, and two Cl atoms. And we end with the same thing. They're just grouped differently. So kind of think about those as the Legos. You're starting off with a magnesium Lego and two HCl Legos. And you end up with a hydrogen Lego and a magnesium chloride Lego. So you're taking the Legos apart and putting them back together in a different way. Whereas in a nuclear reaction, this is an example of a beta decay nuclear reaction. We start with a sulfur atom, and we end up with a chlorine atom. So we're actually making a new type of Lego. The atom itself is changed. And we all know when you're changing your type of atom, that means you're changing your nucleus. So that's why. Notice how there's no chlorine in the beginning and there's no sulfur in the end. You're changing your building blocks. You're changing your element. Okay, does that make sense? Do you guys see how those are very different? So these are just rearranging, and these are totally different elements that are produced. All right. So not all isotopes are radioactive. So this graph should be familiar to you guys. We've got this, we've been using this graph for the last couple classes. So the most abundant one is the one that's shaded dark. Other isotopes are shaded light. Now the radioactive isotopes in this graph aren't shaded at all. They're the empty boxes. So those ones are the ones that are radioactive. Notice as you get bigger and bigger and bigger, you have more and more radioactive isotopes. And hopefully when we watch the Island of Stability, we'll be able to understand a little more about why. So moving forward, you don't have to copy this down. What causes radioactive decay is you have an unstable ratio of neutrons and protons. As you notice, if you look up, this line represents 1 proton per neutron. So as you get to be larger and larger, you need more and more neutrons per proton. So when you get to something like 80 protons, you need about 3 neutrons for every 2 protons. So you have to have more and more neutrons to hold those protons together. So that was interesting. So alpha and beta decay are 2 common types of nuclear radiation. So when you have this unstable neutrons and protons in the nucleus, these are 2 of the ways that the nucleus will break up. You don't have to write the last bullet point. So alpha and beta decay are 2 very common types that are actually going on right now as we speak. Alpha particle, alpha decay is a helium nucleus that's emitted from the nucleus of the atom. And a beta particle is an electron that's emitted from the nucleus with high energy. The alpha particle is a lot bigger than the beta particle, as we talk about. An alpha particle is made of 2 protons and 2 neutrons. And there are a lot more that we don't cover in this class. These are just two basic ones. We'll talk about a couple more later. So moving forward, you have this chart in the introduction to nuclear chem worksheet that I just passed out, so there's no need to copy it. And alpha, this is just alpha particle. This is the symbol. It's 4,2He. 2 protons and a total mass of 4. So it has 2 protons, 2 neutrons. This is the beach ball of nuclear particles. It's like you're getting hit with these right now, all the time. But imagine getting hit with a beach ball. Does it hurt? What's up, Cassidy?
This number, like, the 4, that's neutrons?
Nope, that's the mass.
Okay.
The
neutrons would be 4, like, minus.
Yep. The neutrons is the difference between mass and protons. A beta particle is like the baseball of nuclear decay. If you can imagine getting hit with a baseball, that hurts, right? That does not feel good. And a gamma particle is like the bullet of, and it's actually not a particle at all. It's just high energy. So, moving forward, alpha decay. This is an example when you have this nucleus and it just breaks apart. So notice a couple things. Notice, let's see, does this work? I'm going to try something. So notice you start off with this nucleus right here. Uranium-238. It's unstable, it breaks apart. And it gives off this alpha particle. This is the Greek symbol alpha. That's the Greek letter. Oh. So this here is the alpha particle right here. This is just the symbol, the Greek letter alpha. And so notice a couple things. The mass, total mass is always the same. If you give up 4 mass, you have you start off with 238 mass, and that's equal to 234 plus 4. So my mass I give up in the alpha particle, the rest of that mass is still there. Same thing with this atomic number. I start with 92 protons, I give up 2, and I'm left with 90. 92 is equal to 90 plus 2. And I'm left with atomic number 90. If you guys look in your periodic table, atomic number 90 is thorium. Okay? Makes sense? And beta decay is a little bit different. In beta decay, you have one of the neutrons in the atom, right here. A neutron spontaneously breaks up into a proton and an electron. Interestingly enough, you know how atoms are made of subatomic particles? Subatomic particles are made of sub-subatomic particles. So there's actually things that make up protons and neutrons. And those are called quarks. I don't know if you guys have ever heard that. The term actually came from a James Joyce novel. And he called little things in soup quarks. I don't know. I've never even read the novel, but I know that's where the term came from. So a neutron in the nucleus breaks up into a proton and shoots off the electron. This is the beta particle. The beta particle is that guy right there, that electron that's shot off with a really lot of energy. So an equation for this would be like cesium-137 gives off that particle. If one of the neutrons turns into a proton, I have one more proton than I started off with before. My mass is the same though. Notice the similar thing with alpha. The masses add up as well. So you know that 137 plus 0 is 137. You know that 56 plus negative 1 equals 55. All right. So let me pause it for a sec. So I want you guys right now to try to predict what the other product are. And I'll start us off. So remember, carbon 14, C14, carbon 14, and uranium-238 is U-238. So if you're giving up a beta particle, that means you're giving up 0, -1 E. If you're giving up an alpha particle, that means you're giving up 4, 2 He. This is the alpha particle.
Every time?
Every time this is alpha. Alpha emission. Emission just means to give up. So whenever you're talking about alpha emission, you're talking about this particle right here. Whenever you're talking about beta emission, you're talking about this particle right here. This is the beta particle, this whole thing. Okay? So let's pause it for a second, see what you guys can come up with. You guys are going to need your periodic tables. So, first off, what's the atomic number of calcium, Divine? Do you have your periodic table? Carbon. Carbon.
Is that a 0?
Yep. Carbon is what? 6. So carbon's 6. So I'm going to make another product. My mass was started off as 14, and I gave up 0. What's left? 14.
Wait, say that again?
I started off with a mass of 14, and I gave up 0. Right? Start off with 14, changed by 0, so my mass is 14. I start off with 6 protons. One of my neutrons changed into a proton. So how many protons do I have left? Really? I had started off with 6 protons, and I gained a proton.
7.
I have 7.
Wait, why did you gain one if it's negative?
I know.
Hold on.
How'd you even get that?
Think about it. I start this here. Start off with 6 protons.
Oh, since it's beta emission?
How many neutrons? How many neutrons are in this one? No. How do I find neutrons? 8 neutrons. One of my neutrons became a proton. So how many protons are left? I have 8 neutrons and 6 protons. One of these neutrons became 1 proton.
7.
So I have 7 protons and 7 neutrons. So my mass is 14, 7 protons. What element is this? This is why you need your periodic table. What's atomic number 7?
Nitrogen.
Nitrogen. Boom. Now check it out. 14 equals 0 plus 14, right? 14 is equal to 0 plus 14, correct?
Yeah.
7, no giving up. 7 plus -1, is that equal to 6? 7 minus 1?
Yeah.
6. I'm good. Check it off. Uranium-238. What's uranium's atomic number, Anthony? Come on, you haven't. Get your periodic tables out. Come on, guys. Get out your periodic tables. What is it? 92. So, Carla, I started off with a mass of 238, and I gave up 4. What's left? 234. I started with 92 protons. I gave up 2. What's left? 90. What's atomic number 90? You haven't memorized them yet?
Wait, I have a question.
Neither have I. Hold on, one sec. What's atomic number 90?
Like thorium 1.
Thorium. Boom. Let's check it out. 238, is that equal to 4 plus 234? Yep. 92, is that equal to 2 plus 90? Check. We're good.
That's it.
Bingo. That's all you gotta do.